My name is Hunter Lauber, and my report is on computational genomes, how far they have come, and technologies that they are now leading to. Computational genomes refer to the use of computers when creating genomes. They were first introduced in 2006 and have become the #1 way of sequencing genomes. What used to take 13 years and over $1 billion could now be done for around $1,000 in less than 2 days. This image shows the difference of the amount of data obtained between the old way of sequencing, the Sanger sequencing method, and next-gen sequencing. The computers run through algorithms to match patterns, use mathematical models, image processing, and other ways to find the meaning of sequence data. This data would then be uploaded to a database and become a pangenome. A pangenome, according to the Computational Pangenomics Consortium, is defined as a public database containing an assessment of genomes and transcriptomes, alterations in major types of tumors, tissues, and experimental models. This technology keeps getting more advanced, which keeps driving what we can do with DNA sequencing further and further. The 23andMe tests are a notable example of how the technology is advancing. In 2001, it would have taken forever to sequence one person's DNA. Now we can do it in a matter of days and for cheap. So what is next? With this technology, we have come to understand DNA at a new level. We can start to do things with DNA that we could have never dreamed of with the knowledge we have obtained thanks to next-gen DNA sequencing. We have taken a step into using DNA to store data. According to an article written by Alex Cabral and published by Harvard, DNA is incredible with its potential to store information and encode for the information with a DNA sequence. This has led large corporations to use DNA for storage of data. Alex Cabral in the same article states that Microsoft and the University of Washington were successful in storing 200 megabytes of data using DNA that was made synthetically. According to David Grossman, an article published by Popular Mechanics, with this technology, the entire database of YouTube could be stored in a teaspoon of DNA. So how does it work? Basically, what is happening is data is converted to a binary sequence consisting of zeros and ones. This is the most effective way of doing it as of now. It has also been tried to convert to the alphabet into sequencing through reading frames, which would have resulted only 3 nucleotides needed. But it was less effective at reproducing the data than binary, and it led to many errors that basically made the DNA unreadable. Each nucleotide can represent 2 numbers of binary sequencing. This is the best way to get around homopolynucleotides. These sets of nucleotides are long tracks of single nucleotides that are prone to error. These would become a problem if a single nucleotide would code for one number, resulting in a potential spot for error. With the nucleotides representing binary code, we can begin to synthesize DNA that corresponds to that code. Nucleotides are combined piece by piece after the code is converted by a computer to create the DNA storage. Now there are some problems with the storage and there are some problems with storing data in DNA. Errors are one of the main concerns with this type of storage because DNA can make errors that could corrupt the data. Along with this, setting up the coding for one nucleotide to equal 2 numbers, there is another way to help stop errors from occurring. Producing many copies of DNA can help to avoid corrupted data and make sure that the information is safe in DNA form. This is because the more amount of DNA, then the more likely you are to have one that didn't have any errors, so it would be readable. From here, the DNA must be stored. It cannot just be left out and not degrade. This is where the limitations of DNA storage start to show through. DNA oleo libraries, which are chips that hold DNA, are thought to be the best way to store DNA data. The DNA would have to be separated into 200 base pair strands and put into separate oleo pools. This would result in about 4,000 bytes of memory per pole. This is an image of DNA oleo library. Each one of these cells would be able to hold 200 base pairs of synthesized DNA, so each one would be able to hold 400 bits of memory, which is about 500 bytes. So now the DNA is stored. What is next? To convert the DNA back into data, the same technology is used as before to sequence the DNA. Next-gen sequencing to allows us to read the DNA fast and efficiently. As sequencing becomes faster, this technology of DNA storage will become increasingly more useful, allowing for mass storage of data in DNA. This technology could completely change how we store data and the future of hard drives. If we keep pushing it, it could lead to the current data storage becoming obsolete because of how much more efficient storing data in DNA could become. The only ethical problem would be the people that view DNA as something not to mess with in the way that we are doing here. However, the DNA used in DNA storage is synthetic, so it is not taken from anything living. I think this technology could become a normal part of the future with the size of a technological leap that it could lead to. I think that this is a great technology that could lead to a better future.